A Short History of Nearly Everything by Bill Bryson. Welcome, friend. Seriously, congratulations on making it here. And I mean that more literally than you might think. Because here's the thing, you almost didn't exist. For you to be sitting here right now, trillions upon trillions of atoms had to drift through the cosmos, meet at precisely the right moment, and assemble themselves into the gloriously improbable arrangement that is you. It's a combination so unique, so particular, that it has never happened before in the entire history of the universe, and it will never happen again. And for the next several decades, these microscopic particles will quietly go about the business of keeping you alive, allowing you to experience something most of the universe never gets to enjoy: the strange privilege of being conscious. Pretty wild way to start a book, right? That's the opening to A Short History of Nearly Everything, written by a guy named Bill Bryson, who changed how millions of people think about, well, everything. Now, Bill Bryson isn't some lab coat-wearing scientist. For most of his career, he was just a travel writer with a knack for noticing the absurd and charming details of the places he visited. But one day, stuck on a long flight over the Pacific Ocean, staring out the window at moonlight glinting off the water below, something uncomfortable dawned on him. He didn't know the first thing about the only planet he'd ever call home. Why were oceans salty but the Great Lakes weren't? What the heck was a proton? A protein? Was a quark some kind of cheese? He realized, in his own words, that he'd become an incurious lump, so he decided to fix that. He spent 3 years diving into science books, tracking down patient experts willing to answer his endless questions, all with one goal: to see if it's actually possible to understand and enjoy the wonder of science without drowning in jargon and equations. The result? A Short History of Nearly Everything became an international phenomenon, selling millions of copies and proving that the story of the universe isn't reserved for people with PhDs. It belongs to all of us. Today, we're going on that same journey. By the time we're done, you'll understand how we went from literally nothing to the thinking, feeling, bizarrely self-aware creature that is you. You'll learn about the secrets hiding inside atoms, the hilariously petty feuds between Victorian dinosaur hunters, and the sheer, mind-boggling luck required for any of us to exist at all. This isn't just a summary, it's an invitation to see the world with fresh eyes and maybe feel a little more amazed by the fact that you're here at all. Let's dive in. Our story begins before beginnings were even a thing. Before time, before space, before anything you could remotely call a thing. Picture a point so impossibly small that it makes the period at the end of this sentence look like a planet. Now imagine cramming every single atom in the entire universe, every star, every galaxy, every speck of cosmic dust, into that point. This is what scientists call a singularity. And there's no outside it, no darkness surrounding it, no empty void. The singularity doesn't exist in space, because space doesn't exist yet. Time doesn't exist either. There's no before for it to emerge from. Then, in one blinding instant, faster than you can snap your fingers, faster than you can blink, everything explodes into existence. In the very first second, gravity appears. The fundamental forces of physics snap into place. In less than a minute, the universe has expanded to 1,000,000 billion miles across. Within 3 minutes, 98% of all the matter that will ever exist has been created. Boom, you've got a universe. All in roughly the time it takes to make a sandwich. Now, this whole Big Bang idea is surprisingly recent. It didn't really catch on until the mid-1960s, when two radio astronomers in New Jersey stumbled into one of the most important discoveries in human history completely by accident. Their names were Arno Penzias and Robert Wilson, and they were working with a massive communications antenna, but they kept hearing this annoying hiss. A constant, static-like noise coming from every direction in the sky, day and night, all year round. For a year they tried everything to get rid of it. They checked every wire, rebuilt equipment, and even climbed into the giant dish to scrub out what they politely called white dielectric material, bird poop, basically. Nothing worked. Meanwhile, just 30 miles away at Princeton, a team of scientists was desperately trying to find the very thing Penzias and Wilson were trying to eliminate. A physicist named George Gamow had predicted years earlier that if the Big Bang really happened, it would have left behind a faint afterglow, an echo of creation itself, still detectable as microwaves. That irritating hiss, that was the echo. Penzias and Wilson had found the edge of the visible universe. They were hearing the birth cry of creation itself. In fact, if you've ever tuned a television to a dead channel and seen that dancing static, about 1% of it is leftover radiation from the Big Bang. You've literally seen the dawn of time. The discovery proved the universe had a beginning. But it revealed something even more mind-blowing. The universe is perfectly, impossibly fine-tuned for us. If gravity had been just a tiny bit stronger or weaker, if the expansion had been even slightly faster or slower, stable matter wouldn't have formed. The universe would have either collapsed immediately or scattered into eternal emptiness. Scientists call this the Goldilocks effect. Everything is just right. Some experts think this means there may have been trillions of other Big Bangs, and we just happen to exist in the one that got the settings right. As one scientist put it, our universe is simply one of those things which happen from time to time. But creating a universe was just step one. The Big Bang only made the lightest elements: hydrogen, helium, a little lithium. It didn't create the heavy stuff we're made of, like carbon, nitrogen, and oxygen. So where did those come from? Enter Fred Hoyle, a brilliant and famously stubborn English cosmologist. Ironically, Hoyle actually hated the Big Bang theory. In fact, he coined the term Big Bang sarcastically during a radio interview. But he had a revolutionary idea. He realized that when a massive star, much bigger than our sun, reaches the end of its life, it collapses inward and then explodes in a spectacular blast. He called this a supernova. In that instant, a supernova releases the energy of 100 billion suns, briefly shining brighter than an entire galaxy. The heat is so intense, over 100 million degrees, that it forges heavier elements. These new elements then spray across space, forming clouds that eventually collapse into new solar systems and planets. Every carbon atom in your body, every molecule of oxygen you breathe, every trace of iron in your blood was forged in the heart of a dying star billions of years ago. You are, quite literally, made of stardust. About 4.6 billion years ago, a swirling cloud of this star stuff began gathering in our little corner of the galaxy. Almost all of it, 99.9%, went into making the sun. Out of the leftover scraps, tiny dust grains collided and stuck together. Over millions of years, these clumps grew into baby planets. One of them was Earth, formed in just 200 million years, though it started as a molten hellscape, constantly pummeled by space debris. Then something catastrophic happened. An object the size of Mars slammed into Earth, blowing out enough material to form a companion sphere, the Moon. This colossal impact is why the Moon has so little iron, while Earth has lots. Most of the material came from Earth's rocky crust, not its iron core. Young Earth was brutally hostile. The atmosphere was a toxic soup of carbon dioxide, nitrogen, and sulfur. The surface was relentlessly bombarded by comets and meteorites, which, fortunately, brought water to fill our oceans and the chemical ingredients for life. And then, in this violent, chaotic world, something extraordinary happened. A tiny bag of chemicals twitched and became alive. We were on our way. For billions of years, that unbroken thread of life has continued in a world whose sheer scale is almost beyond comprehension. Let's take a quick tour of our cosmic neighborhood to get a sense of just how mind-bendingly big it is. If you've ever seen one of those solar system charts in a classroom, you've been lied to. Those neat diagrams showing planets spaced at friendly intervals are necessary deceptions to fit everything on one page. The reality? Space is stupidly, absurdly enormous. If you shrunk Earth down to the size of a pea, Jupiter would be over 1,000 feet away, and Pluto would be 1.5 miles distant, about the size of a bacterium, so you couldn't even see it. On that same scale, the nearest star, Proxima Centauri, would be 10,000 miles away. Space, I'll say it again, is ridiculously enormous. Our entire solar system, the Sun, all the planets, their moons, asteroids, everything, fills less than 1/1,000,000th of the available space. It's emptiness beyond comprehension. And in all that emptiness, we've had to piece together our understanding of the universe through human ingenuity, stubborn persistence, and sometimes outright weirdness. Take the simple question of Earth's size. In the 1730s, a team of French scientists traveled all the way to Peru to measure 1 degree of Earth's meridian. The expedition was a complete disaster. Their doctor was murdered. Their botanist went insane. The leaders stopped speaking to each other. They spent nearly a decade in brutal conditions, only to learn that another team back in Europe had already figured it out. It's a reminder that science is messy, human, full of ego and error. But out of that mess came clarity. And at the heart of it all stood a man who was brilliant beyond measure, but also joyless, solitary, and spectacularly strange. Isaac Newton. In the 1680s, the astronomer Edmund Halley visited Newton at Cambridge with a burning question that nobody could answer. Why do planets move in ellipses? Newton replied immediately that of course they'd move in ellipses. When Halley, stunned, asked how he knew, Newton said simply, "Why, I have calculated it." But then he couldn't find his calculations. Imagine someone telling you they'd cured cancer, but couldn't remember where they put the formula. Pressed by Halley, Newton agreed to redo the work. He then vanished for 2 years of intense thought and emerged with his masterpiece, the Principia. It was a book that changed everything. It laid out the 3 laws of motion and the universal law of gravitation. It explained why oceans have tides, why cannonballs arc, and why we don't fly off the planet as it spins. Suddenly, every motion in the universe made sense. But the Principia also contained a puzzle. It suggested that if you could measure a mountain's gravitational pull, you could calculate Earth's entire mass. But who could perform such a delicate experiment? Enter Henry Cavendish, one of the most brilliant and bizarre scientists who ever lived. Born into immense wealth, Cavendish was pathologically shy. He couldn't stand being looked at or spoken to. He communicated with his housekeeper through written notes. But the man was a genius. He discovered or anticipated the law of conservation of energy, Ohm's law, Charles's law of gases, and much more, but told no one. Most of his discoveries weren't known until a century after his death. In the late 1790s, Cavendish set out to weigh the Earth. Using an ingenious but incredibly delicate apparatus of suspended lead balls, he spent nearly a year making painstaking observations from an adjoining room, peering through a telescope. When he finally finished, he announced that Earth weighed just over 6 billion trillion metric tons. Today, with machines so sensitive they can detect a single bacterium's weight, scientists haven't significantly improved on Cavendish's measurement from over 200 years ago. By the early 1800s, we knew Earth's shape, size, and weight, but how old was it? That question would spark one of science's fiercest battles. The man who started it all was James Hutton, a Scottish gentleman farmer. Hutton realized that Earth's features, mountains, valleys, coastlines, weren't static. They were shaped by slow, relentless processes of erosion and uplift, acting over immense spans of time. His theories suggested Earth had to be incredibly ancient. Unfortunately, Hutton was almost completely incapable of writing a clear sentence. His books were so unreadable, his ideas went almost unnoticed. Luckily, his friend John Playfair rewrote his work in plain English, and slowly the world began awakening to deep time. Geology became the hottest science of the 19th century. Gentlemen in top hats ventured into the countryside for a bit of stone-breaking, and they were gripped by controversy: catastrophism versus uniformitarianism. Catastrophists believed Earth was shaped by sudden, violent events like the biblical flood. Uniformitarians, led by the great geologist Charles Lyell, believed all changes were gradual, happening slowly over eons. Lyell's ideas became geology's foundation, but they created a massive problem. In 1859, Charles Darwin published On the Origin of Species. His theory of natural selection required vast amounts of time for evolution to work. But the greatest physicist of the age, Lord Kelvin, insisted it was impossible. Based on thermodynamics, he calculated the sun could be no more than a few tens of millions of years old. If the sun was young, Earth had to be young. Darwin's theory couldn't work. For decades, science was deadlocked. Geologists and biologists needed an old Earth, but physicists wouldn't budge. The answer, when it came, was revolutionary: radioactivity. In 1904, a young New Zealand physicist named Ernest Rutherford realized that radioactive decay inside Earth provided a heat source Kelvin hadn't accounted for. This meant Earth could be far, far older than anyone imagined. Rutherford also noticed radioactive materials decay at steady, reliable rates, their half-life. This meant they could be used as clocks. By measuring uranium's decay into lead, scientists could finally date rocks. An English professor named Arthur Holmes spent decades patiently refining this technique. By the 1940s, he could confidently announce Earth was at least 3 billion years old. But the definitive answer came from a graduate student in Chicago named Claire Patterson. He spent 7 years in a sterile lab, precisely measuring lead-to-uranium ratios in ancient meteorites, leftover building materials from the early solar system. In 1953, he announced Earth's age, 4.55 billion years. That number stands unchanged today. But Patterson's work led him to a disturbing discovery. His samples kept getting contaminated by atmospheric lead. He realized we'd been pumping massive amounts of lead into the air through leaded gasoline. He then devoted his life to a heroic, lonely campaign to get lead removed from gasoline, fighting powerful corporations and even the government. He eventually succeeded, and lead levels in Americans' blood fell by 80%. He may have been the 20th century's most influential and least known geologist. The discovery of deep time and radioactivity opened two new frontiers, the very large and the very small. While astronomers like Edwin Hubble discovered the universe was expanding and filled with billions of galaxies, physicists were journeying into the atom's heart. The atom's story is among the strangest in science. Ernest Rutherford provided the first real evidence of its structure by firing alpha particles at gold foil. He was astonished when some bounced straight back. It was, he said, like firing a cannonball at tissue paper and having it ricochet back at you. He realized atoms were mostly empty space with a tiny, dense nucleus at the center. This created a huge problem. By all known physics, atoms shouldn't exist. Electrons orbiting the nucleus should quickly lose energy and spiral inward, with disastrous results. A young Dane named Niels Bohr solved this by proposing the quantum leap. Electrons could jump from one orbit to another without visiting the space between. It was utterly bizarre, but it worked. It opened the door to quantum mechanics, a world where things can be in two places at once, where particles pop into existence from nothing, and where uncertainty is fundamental. As physicist Richard Feynman said, things on a small scale behave nothing like things on a large scale. It's a world our brains just aren't wired to understand. From this weird world came the standard model of particle physics, a kind of parts catalog for the subatomic world, with quarks, leptons, and bosons. It's elegant but messy, explaining three of the four fundamental forces: strong and weak nuclear forces and electromagnetism. But it says nothing about the fourth, gravity. For that, we turn back to Albert Einstein. Einstein's general relativity describes gravity not as a force, but as a byproduct of warped spacetime. Massive objects like the Sun create dips in the cosmic fabric, and planets simply roll along the curves. It's beautiful and explains the large-scale universe perfectly, but it has no influence at the particle level. So physics ended up with two sets of laws, one for the very small, one for the very large, that don't talk to each other. Einstein spent the rest of his life searching for a grand unified theory to tie them together. He never succeeded. It remains physics' greatest challenge today. With this new understanding of time and matter, the final piece fell into place: the story of life itself. It starts with a single cell. The idea that all living things are made of cells is modern biology's foundation, but it wasn't proven until the 1860s that life cannot arise spontaneously. It must come from pre-existing cells. Robert Hooke first described a cell in 1665. But a Dutch linen draper named Antonie van Leeuwenhoek revealed the microscopic world's true wonder. With his simple but powerful microscopes, he discovered protozoa and bacteria, revealing a universe of life no one suspected existed. Today, we know every cell is a miniature city. Inside each one, millions of proteins zip about, performing thousands of tasks per second. It's ceaseless, frantic activity, all directed by a curious, determined molecule that isn't itself alive. DNA. How we unraveled DNA's secret is one of science's great dramas. For years, scientists thought proteins had to be heredity's key because DNA seemed too simple. But in 1944, a quiet scientist named Oswald Avery proved DNA was the active agent. The race was on to find its structure. Victory fell to two young Cambridge scientists, James Watson and Francis Crick. Their breakthrough crucially depended on Rosalind Franklin's work at King's College London. She had the best DNA X-ray images in existence. When her colleague Maurice Wilkins showed her images to Watson without her knowledge, it gave them the final clue. In 1953, they unveiled the double helix model, and life's secret was revealed. What they'd found was a molecule that could replicate itself with incredible speed and accuracy. It was the body's instruction manual. But it also revealed something profound. 97% of our DNA doesn't seem to do anything. It's junk DNA. Life's purpose, in a sense, is simply to perpetuate DNA. We're just vessels for its continuation. Even more surprising, life uses a single set of blueprints. Over 60% of human genes are the same as fruit fly genes. About half the chemical functions in a banana are the same as in you. All life is one. It's the most profound true statement there is. This brings us to our own story, the rise of the mysterious biped. For 99.999% of our history, we shared an ancestral line with chimpanzees. Then, about 7 million years ago, new beings emerged in Africa, the Australopithecines. They walked upright, but for millions of years their brains didn't grow, and they didn't use tools. The most famous is Lucy, a 3.18-million-year-old skeleton found in Ethiopia. She was tiny, just 3.5 feet tall. For a long time, she was thought to be our direct ancestor, but now many experts aren't so sure. The story's much messier. It seems there were as many as 6 types of hominids coexisting in Africa, and only one lasted, the genus Homo. It begins with Homo habilis, the first tool user, and then, about 1.8 million years ago, came Homo erectus. Erectus was a game-changer. The first to hunt, the first to use fire, the first to leave Africa. Long-limbed, lean, and very strong. To other hominids, it must have seemed terrifyingly gifted. Then, somewhere over 100,000 years ago, Homo sapiens us arose on the African plains. The traditional story is we spread out in a second wave, displacing all older hominids like the Neanderthals in Europe. This is the out-of-Africa theory. But there's an alternative called multi-regionalism, championed by Alan Thorne in Australia. It holds that human evolution was continuous, that Homo erectus in different regions simply evolved into modern humans. The evidence is confusing and hotly debated. Genetic studies of mitochondrial DNA seem to support out of Africa, suggesting all modern humans descended from a small founding population in Africa. But then, in 2001, DNA recovered from a 62,000-year-old skeleton in Australia, Mungo Man, was found genetically distinct, a lineage now extinct. It turned everything upside down. The truth is likely a messy combination of both theories, with multiple migrations and lots of interbreeding. We're just beginning to understand our own tangled story. What's certain is that from the Big Bang to that first twitch of life, to the long journey to consciousness, our existence has been a nearly endless string of good fortune. We're here because of a chain of events so improbable it borders on miraculous. Each of us is a testament to an unbroken lineage stretching back 4 billion years. Think about it. Through every ice age, every asteroid impact, every pandemic, every predator attack, every single one of your ancestors survived long enough to reproduce. We are the children of survivors. And we are, as far as we know, the only beings in the universe capable of looking back at this long, strange journey and appreciating its wonder. It's unnerving to think we may be the living universe's supreme achievement and its worst nightmare simultaneously. We've been chosen, by fate or chance, to be custodians of life on this lonely planet. The trick, of course, is making sure we never find the end of the story. As we reach the end of this journey through a short history of nearly everything, It's worth pausing to reflect on what this really means. This isn't just a collection of science facts. It's a story about us. It's a lesson in profound humility and gratitude. The single most powerful idea running through this entire book is the sheer, breathtaking improbability of our existence. The universe didn't have to exist. Life didn't have to arise on this planet. And we, thinking, feeling, wondering human beings, certainly didn't have to be here. Yet here we are. We're the result of a chain of events so long, so complex, and so ridiculously lucky that it's impossible to contemplate without awe. Think about that Goldilocks effect we talked about earlier. If the fundamental forces had been just a fraction different, no stars would have formed, no planets, no life. Think about the asteroid that wiped out the dinosaurs. Had it been slightly smaller, or arrived a few minutes earlier or later, dinosaurs might still roam the Earth, and our mammalian ancestors would still be tiny, timid creatures hiding in the shadows. We're here because of cosmic accidents and timely flukes. And we're not just any life form. We're the one species, as far as we know, that's developed the capacity to understand the universe that created us. As Richard Feynman put it, a physicist is the atom's way of thinking about atoms. We're the universe's way of knowing itself. That's an incredible privilege, and it comes with profound responsibility. The story of science, as Bill Bryson tells it, is also a story of human fallibility. We've been arrogant, short-sighted, and often spectacularly wrong. We've been slow to accept new ideas and quick to dismiss challengers. We've been careless with our planet and the species sharing it with us. Yet it's also a story of incredible triumph. The human mind, with its insatiable curiosity, has unpicked the cosmos's deepest secrets. We've weighed the Earth, dated its rocks, and read life's story written in stone. We've journeyed into the atom's heart and peered back to time's dawn. So what can we take from this grand story? How can we apply these lessons to our lives? First, cultivate wonder. Next time you're outside on a clear night, look up at the stars. Don't just see distant points of light. See them for what they are. The furnaces where the atoms making up your body were forged. Think about the immense, unimaginable distances their light traveled to reach your eyes. You're looking at history. Second, cultivate humility. Pick up a rock, hold it. This simple object has been on a journey that makes our lives seem like the briefest flicker. It's been melted, crushed, weathered, and reformed over eons. It holds a story of deep time we can barely begin to read. It reminds us we're a small part of a much larger, much older story. Finally, cultivate gratitude. Think about the trillions of cells working tirelessly inside you right now. They're the legacy of an unbroken chain of life stretching back 4 billion years. Every one of your ancestors, through unimaginable hardships, survived and passed on the gift of existence. You're the culmination of that incredible journey. That was a summary of A Short History of Nearly Everything by Bill Bryson. We've hit the highlights, but honestly, a summary can only take you so far. The real magic happens when you read the book yourself. It's in the quiet moments when a particular story or simple phrase hits you unexpectedly. This summary is designed to help you decide if this book's worth your time. If anything we've talked about today resonated with you, I wholeheartedly encourage you to grab a copy. Reading it isn't just learning. It's an experience that can genuinely change how you see yourself and your place in this vast, beautiful, utterly mysterious universe. Also, if you found this journey valuable, please consider subscribing to the channel so you won't miss our next exploration into another life-changing book. Let's keep growing together, one story at a time.